In this video, we're going to talk about acids and bases. Now, acids were originally defined as substances that taste sour. Obviously, that's not the best definition of an acid. So Arrhenius came along and defined an acid as a substance that produces hydrogen ion when it dissolves in water. So an example might be something like HCl. When we dissolve it in water, it becomes H plus and Cl. So it produces that hydrogen. And then bases are also a class of chemical compounds, and they were originally defined as substances that taste bitter. Again, not the best definition of a base. You don't want to go around and taste things to see if it tastes bitter and then decide that it is a base. Arrhenius came along, and an Arrhenius base is defined as a substance that produces hydroxide when dissolved in water. Now, there are some weaknesses to this because ammonia does not have hydroxide. Something like sodium hydroxide, when dissolved in water, will produce hydroxide. But if we don't even have hydroxide in our base, then not everything that can act as a base will produce hydroxide. So Bronsted-Lowry came along and defined an acid. Bronsted-Lowry is something that donates a proton. Remember, in chemistry, a lot of times we refer to hydrogen ion as a proton because that's all that is in it. So the acid is something that donates the proton. The Bronsted-Lowry base is something that accepts that proton from another molecule. So if we look at the dissociation of HCl in water, HCl is my acid. That means the water has to be my base. HCl is going to donate this proton and give it to water. Since water is acting as my base, it's going to accept that proton. So when HCl donates that proton to water, the water becomes H3O plus, and the hydrochloric acid becomes chloride as soon as it loses that proton. Conjugate acids and bases are always the product. They're always the products. So when we look at the definition of a conjugate acid or a conjugate base, you have to look at where it comes from. So when the Bronsted-Lowry base accepts a hydrogen, it becomes the conjugate acid. And when the Bronsted-Lowry acid donates a proton, that is the conjugate. Notice conjugate acid and conjugate base are the results the acid and the base donating or accepting the proton. So they're always going to be the product. The conjugate acid base pair are the two molecules together. So again, let's look at the dissociation of HCl in water. We just did this example, and we said that HCl is our acid and water is going to be acting as our base. HCl is going to donate a proton to water to become hydronium ion. So the HCl donates the proton to the base, water. And as a result, we get our conjugate acid. Since HCl donates the proton, it gives its proton away and it's left with chloride, which is going to be our conjugate. Now remember, the definition of an acid is that it donates a proton. So that means it has a hydrogen. If something doesn't have a hydrogen, then it cannot be a base. So for that reason, if your anion is present and it does not have any hydrogens, then there's no way it can be any type of acid because the definition of an acid is that it donates a proton. If you don't have a proton, you can't be an acid. Let's look at then base. So a strong or base or a strong base will completely dissociate in water. We have 7 strong acids in this class, and you must know these. They are HCl, HBr, HI, so hydrochloric acid, hydrobromic acid, hydroiodic acid, and then we have nitric acid, sulfuric acid, perchloric acid, and then we also have, so those are the strong acids for this class. You must know those. To determine the weak acids, they are going to be everything else. Now, there are other strong acids. We just don't cover them in this class. These are the only ones that you're required to know for this class. Remember, a strong acid completely dissociates in water. So if we have something like HBr, it is going to completely dissociate into ions. So in solution, we only have ions. Remember, strong acids also behave as strong electrolytes. We are also going to talk about 6 strong bases in this class, and they are all going to be hydroxide. So you have to look at the soluble hydroxide. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, and then from potassium on the periodic table, go directly over to group 2, and we will have calcium hydroxide, calcium hydroxide, and barium. And we stop at barium because if someone drinks barium hydroxide, you're going to have to barium. All right, so an example of a strong base like lithium hydroxide, when you dissolve it in water, it completely dissociates into ions. So in solution, we only have the weak bases, like the weak acids, everything else. Now, just like with the strong acids, there are other strong bases. They're just not covered in this. You do not need to know them. So, Since we have these going to completion, a weak acid, the definition of a weak acid or a weak base is that they do not completely dissociate in water. If we look at an example of a weak acid, HF, it's going to follow the same pattern in that the hydrofluoric acid is going to donate a proton to the water so that it becomes H3O plus, and conjugate base is F minus. But to show that it is a weak acid, because if we left it like this, it looks exactly like a strong acid because we show a complete dissociation. To show that it is a weak acid, we have to put in our equilibrium. So just like a weak electrolyte, weak acids and weak bases exist in equilibrium. So for that reason, we can write an equilibrium expression for an acid and a base. Ka is the equilibrium constant for an acid. Little a just means acid, and Kb, yep, you got it. It is the equilibrium constant base. So because these weak acids and weak bases exist in equilibrium, they don't have that complete dissociation, we can write equilibrium expressions. So let's look at an example. Write the Ka expressions for H2CO3, ammonium, and phosphorus. So we're looking at carbonic acid, ammonium, and phosphorus. One of the best things you can do when you're writing an equilibrium expression is make sure you have a balanced chemical equation. So we have carbonic acid, and we're looking at the dissociation in water. Carbonic acid is my acid. It's going to donate a proton to the water. So we will get hydronium ion, and then I'm going to take one proton away from the carbonic acid. So instead of having two, I'm only going to write one. Now, since I took away a positively charged proton, if you will, that means my overall charge is going to decrease by one. Something I want to point out is the overall charge of my reactants is zero. Overall charge of my products is also zero. When you're looking at these dissociation reactions, whatever the charge, the overall charge of your reactants is, that needs to be equal to the overall charge of your product. That's a way you can double check to see if you're doing these correctly. Now, to write the Ka for this, we are just going to write it exactly like we do all of our other equilibrium expressions. We do the concentration of the product divided by the concentration of our reactant. And remember, water is a liquid. So we do not include that in our equilibrium expression. Whenever you have a Ka, this means you're dealing with an acid. So that means these are going to be behaving as an acid. Whenever you have an acid dissociating in water, your product is always going to be hydronium ion and the conjugate base. When you're visualizing what the conjugate base is going to be, just imagine number of protons decreasing by one. So I can write the Ka, the equilibrium expression for ammonium without even writing the overall balanced chemical equation. And that's because it's always going to be products over reactants. I know my products for the dissociation of an acid is always going to be hydronium ion and the conjugate base. For ammonium, we're going to have hydronium ion, and the conjugate base is going to be one proton less than NH4 plus. I'm going to have NH3. Now, since I took away a proton, remember we're going to decrease the charge by 1. So this is going to go from a +1 to neutral. And then we're going to divide that by the concentration of our original. Remember, this is products over reactants. So the overall charge of my reactants, remember, water is a reactant, but it's always charge neutral. So the overall charge of my reactants has to equal the overall charge of my product. My products in this case are +1. My reactants are also +1. If we look at the example of phosphoric acid, the equilibrium expression is going to be equal to the concentration of hydronium ion times the conjugate base of phosphoric acid. So we're going to take one proton away, and that means we need to decrease the charge by 1. We're going to get dihydrogen phosphate divided by concentration of. So this is the dissociation of an acid. We can write the Ka for it because these are all weak acids and they exist in equilibrium. In this next example, we're going to be writing the Kb's. So that means all of these are going to be acting as a base. So let's look at ammonia. And again, we can write out our equilibrium equation. Ammonia is going to be acting as a base, which means in this case, water is going to be acting as an acid. Water is amphoteric, meaning that it can act as an acid or a base, and you will determine whether it acts as an acid or a base depending on its environment. So when it is in a basic environment, water is going to be acting as an acid. When water is in an acidic environment, then it will be acting as a base. Water is acting as an acid in this case, and it reacts with ammonia. So it's going to donate its proton over to ammonia. When ammonia a proton, it will become NH4. We're going to add one proton. And now, since we're adding a proton, we need to increase the charge by 1. Water lost a proton, so I'm going to take one hydrogen away. I'm left with OH. And since it lost that positive thing, it's going to have a -1 charge. So when water is used to dissociate an acid, hydronium ion is always formed. When a base is dissolved in water, then hydroxide will always. My Kb for the dissociation of ammonia is going to be the concentration of ammonium ion times the concentration of hydroxide divided by the concentration. Notice that the overall charge of my reactants is neutral, and the overall charge of my. Now, when you're writing Kb for a base, the products are always going to be hydroxide and the conjugate acid. So if we want to look at the equilibrium expression for the dissociation of bicarbonate, well, I know that hydroxide is always a product. So we're going to look at the concentration of hydroxide. And then when carbonate gains a proton, because remember, it's acting as a base, so it accepts that proton, then we will get H2CO3. We're adding a proton, so the charge is going to go up by 1 and it becomes charge neutral. And we'll divide that by our original base, the concentration of bicarbonate. If we look at the example of sulfate, oh, look at that. This is not Ka. There we go. Kb. If we look at the dissociation or how sulfate acts as a base with water. Again, we're going to get the concentration of hydroxide times the conjugate acid. When sulfate gains a proton, it becomes HSO4 minus. And then we'll divide that our original base, which was SO4 2 minus. Notice that the charge of my products is -2. The charge of my reactants is also -2.